Hi all, welcome to lecture number 16. In today's lecture, we will understand the fundamentals about AC machine. We will discuss about the induction motor, synchronous motor, their constructional detail and their principle of operation. Once we will go through these basic fundamentals, then it will be easier for us to understand the phenomena behind the installation, maintenance and testing of these AC machines. AC machines, they are widely used throughout the world. Almost 80% of the total machines, they are AC in nature. In traction purpose, of course, we are using DC series motor and some specific use are there where we are using DC machines. But in industries, in common commercial world, in for agriculture purpose, even our home, if you consider, just look at the top, you are having one ceiling fan. It is nothing but single phase induction motor. Just think about your place, your home. You might be having a washing machine. Yes, induction motor is used in that. In ACs, we are having compressors. In many handheld machines, we use the AC machines. So, AC machine may be single phase AC machine or three phase AC machine. As far as the speed of rotation is concerned, we are having two types of machines. One is synchronous machine, another one is asynchronous machine, which is known as induction motor. Here, as teaching aid, I am having one dismantled machine in which here we are having the outer part, which is stator of the machine. In industry, you will find many opportunities where you have to dismantle the machine, you have to inspect the interior of the machine, which part is got damaged or what is to be repaired. So, before that, we will understand what is the principle of this machine. Here, the outer part, this is stator. For heat dissipation, we are having fins. Inside this stator, we are having a stator core, this part. This is stator core. And we are having stator windings. These windings are visible. Can you see? These are all windings. So, three phase winding is placed here in this stator core. In three phase winding, we are having three windings distributed 120 degree apart in space. That means, if suppose starting off one winding is, one coil is starting from here, then that conductor is coming from here, it is going back and it is again coming outside. So, suppose this is the starting point and this is the finishing point of that winding. So, we are having three set A dash. Before I will discuss the placement of B dash and C dash, let me explain by a simple example. Suppose, consider this as soft iron piece. Suppose it is a soft iron piece. If I want to make it magnet, then what I will do? After placing some insulation, I will provide one winding like this. Hope this is very clear to you. So, this is the winding. Inside this is iron core. Now, suppose I am connecting DC supply to this coil. DC is being fed. If it is DC and suppose current is entering from this point, this is positive. This is connected to positive, so current is entering like this. So, if you are looking from this end, can you tell me what is the direction of flow of current in this coil? Whether it is anti-clockwise or it is clockwise? Just feel the flow of current. Current is entering from this point. This is the direction of flow. This is the direction of flow. So, looking from your side, is this current anti-clockwise? Yes, you are right. So, if anti-clockwise, that means here north pole will be formed. On this end we will get south pole. If you are looking from here, if the current was entering from this place, then here it is leaving from this end. That means it is clockwise from this end. So, we can create any desired polarity. If we are having one soft iron piece, we want to make this pole as north, we can fix the direction of orientation of the winding such that we will get the desired polarity. Now, MMF, we are having certain current flowing through this coil, we are having number of turns, that means certain ampere turns are produced here. If we are having 1 ampere current flowing through this and we are having 50 turn or say 200 turns, 200 turns and 1 ampere current. What is ampere turn? Current into turn, number of turn. 1 ampere current, 200 turns. Yes, 200 ampere turn. So, suppose I will mark a line like this passing through the center of this coil. Let me assume one scale. One centimeter is equal to 50 ampere turn. 1 centimeter is equal to 50 ampere turns. And how much ampere turns are produced here? 200. That means 200 divided by, what will be the length of the line if I am representing this MMF by one phasor? turns. Our scale is 50 ampere turn is equal to 1 centimeter. Yes, 4 centimeter line will represent this. Now, suppose current flowing through this is now reduced to half. So, what will be the length of this MMF phasor? Number of turns are still 200, current is now 0.5, only 100 ampere turns are produced. So, now length will be reduced to half. If 0 current is flowing, what will be the length of this phasor? 0. Okay. So, if I am feeding DC supply to this coil, I will get constant MMF. So long the number of turns are fixed, current is fixed, we are having fixed MMF. But now suppose I am feeding AC supply to this, AC alternating current, frequency is changing all the time, 50 cycle per second, it is changing. So what will be the magnitude of phasor? Sometimes it is 0, then it is increasing. When the current is maximum through this coil, maximum MMF we are getting, again it will start decreasing, it will become 0 at the end of positive half. Then for negative half, now direction of flow of current is changed, reversed. So now this time we are getting in opposite direction. So the axis of the field is fixed, but the magnitude of MMF, it is changing all the time. Getting it? If we feed single phase supply to a coil, we get pulsating standing field. Let me repeat. When we feed single phase AC supply to this single phase coil, we get pulsating standing field. Pulsating means magnitude of this flux, resultant MMF, which is flux passing through this, it is changing all the time, it is pulsating. Sometimes it is 0, then maximum, increasing up to maximum, coming back, then direction is changed. So it is pulsating. Now, very interesting thing. If I am holding this coil like this, what will be the axis of the field in this case? It will pass through the center. If I am holding this coil like this, now the flux will pulsate in this direction only. If I am placing this like this, rotated 120 degree, now this is the direction of flux. So, here in the 3-phase induction motor or synchronous motor, we as in general we are discussing AC machine, stator, the outer part, it is similar for all the machines, like let it be squirrel cage type 3-phase induction motor, let it be slip ring type induction motor, or it may be synchronous machine. In all the 3 machine, the stator is same. In the stator we are having 3 windings are placed. Now, you will observe that for placement of 3 winding, how many slots we will need? A dash, then at 120 degree B and B dash, and then C and C dash. Total 6 slots are required for placement of 3. But here plenty number of slots are there, and actually the winding is not concentrated at one place, it is distributed. There are certain advantages of distribution of the winding. So, this is distributing winding, but axis we are having 3 axes for 3 different winding. So, we are having terminals like A dash, then B dash, C and C dash. If all these 6 terminals are brought to the terminal box at the top, this is the at the outer part, it is terminal box, it is provided at the top of the machine. So, you can observe 6 terminals are here. So, in these 6 terminals, suppose first, second and third, it is A, B and C, then we are having A dash, B dash and C dash. But it is not so simple in case of connecting it to star delta starter. You will find that if this is A, B, C, this is not A dash, this is A dash, this is B dash, and last one is C dash. In front of A, you are not getting A dash, it is C dash. Of course, you will find 3 strips here, copper strip, connecting strip. These 3 terminals are short circuited. If you just open these terminals, remove these strips, it is neither star nor delta. If you want to make it a star, then place like this, these 3 terminals are short circuited, it is now star connected mode stator. If this point is connected to this to this, and last one is this to this, then it is getting connected in delta. So, this is something about the stator. On the stator we are having 3-phase windings. When we feed 3-phase supply to the stator of this 3-phase induction motor, which type of induction motor? Whose windings are 120 degree apart in space. This is one of the important part. Otherwise, even in transformer, primary winding is there, secondary winding is there. If you see the schematic diagram of 3-phase induction motor and transformer, it is same. But in transformer, we do not get any rotation. Important part is these 3 windings should be placed 120 degree apart in space. That means axis of winding A, this is winding A, conductor starting from here, coming this, then this is the hanging, and then running coming outside again. So, this part is A dash, this is A. Axis will pass through the center. So, we are having 3 coils which are placed 120 degree apart in space, and we are feeding 3 phase supply. As a result of this, you might have already studied in your electrical machine part the production of rotating magnetic field, but here I just want to explain you that where this rotating field is produced. If you get time to open this machine, and let me help with one ball bearing I am having. This is simply bearing, ball bearing. If I am placing this ball here and I am supplying 3 phase supply, when supply is fed, you will observe that this roller will start rotating. This roller will start rotating. Then you can experience, oh yes, this is the place where this magnetic field is produced. So, this experiment is worth doing. Just observe this. You will get the proper insight of the principle of operation of this. Many times I can recall one famous film, Three Idiots, and one dialogue is there. How does induction motor starts? And then the reply comes, oh, then stop. It is very old joke. Even when I was a student at that time, it was also the joke. But this is FAQ, frequently asked question in interview from the candidate of electrical engineering. What is the principle of operation of 3-phase induction motor? And many people, many students, they do not answer it properly. So, step by step, in today's class I am explaining the procedure. We are feeding 3-phase supply to the stator of induction motor, whose windings are 120 degree apart. As a result, what we have observed, we here in this space we get the rotating magnetic field. Rotating magnetic field is produced. Inside this stator, we are having the second part of this machine, which is rotor. So, here this is cage type rotor, this is squirrel cage rotor, this is rotor. So, as far as the parts are concerned, this is the outer part, this is stator. In the stator we are having stator core, and these are the stator windings. This portion is stationary, we are having provision for fixing it on the foundation. Then end covers are there, one coming from this end, one from this end. So, these are the end covers, these are the end covers. And you can observe here, this is the provision for bearings, 2 bearings are placed. Just see, in this rotor part, this is the driving end, this is the non-driving end. Driving end means here the shaft extension is there, pulley may be connected. So, for a small motor it is okay, but for heavy duty machine, for big size, the driving end bearings are roller bearing, they are the roller bearing, whereas NDE bearing, it is ball bearing. Yes, you can observe, you can clearly observe the balls. So, on driving end it is roller bearing, on non-driving end NDE it is ball bearing. And in maintenance, this is one of the common problem. If the after applying proper supply, your machine is not rotating, what to do? Just try to rotate the shaft, whether it is free or jam. If it is not free, then there is no electrical fault. It is similarly some mechanical fault. You have to just open it, properly lubricate and remove the jamming, and it will start rotating freely. So, this part, the central part, this is cage type rotor. Here just you can observe some skewed lines. Actually, the remaining portion, this is made up of aluminum. So, actually in rotor various slots are there and the rotor bars are inserted in this. These rotor bars are skewed like this, and this is the end ring. This is end ring of on the left hand side, on the right hand side. So, we are having two end rings. So, just imagine this is one conductor. Suppose this is aluminum, this is aluminum, this is also aluminum, it is made up of aluminum, this is one conductor. This is another conductor, second conductor, third conductor, fourth conductor. So, we are having plenty number of rotor bars. Have you seen any X-ray film in which you will observe the skeleton, the structure of the human body? If you are having any machine which can scan only aluminum part, then what you will observe? Only one bar here, second bar here, third bar here, fourth. So, only rotor bars you will observe made up of aluminum, and you will observe two end rings at both the end. So, suppose just imagine one cage, rotor bars and end ring is there, at the center one shaft is there. If one small squirrel is kept inside, when she puts her hand on one of the bar, by pressure it will start coming down. So, out of say she tries with other hand, then this way, this way, this way. She keeps on moving her hands, and as a result what happens? The cage of this squirrel, it starts rotating, and the house owner, he enjoyed a lot. So, the structure of this cage is exactly similar to the cage of the squirrel. That is why this particular shape is known as squirrel cage induction motor. So, let me recombine both the parts. If three-phase supply is given to the stator of machine, whose windings are kept 120 degree apart in space, one rotating magnetic field starts in the gap, here it is starting. Inside this stator part, this rotor is inserted. Now, the magnetic field, it is cutting these conductors. Magnetic field, it is when it sweeps past the conductors, there is a relative motion between this conductor and the magnetic field. Magnetic field is rotating, conductors are stationary. As a result, what will happen? EMF will be induced in these conductors. If these two end rings are not present, we are having suppose one conductor, EMF is induced in this conductor. That means, suppose this point is at higher potential, this point is at lower potential. We are having other conductor, this point is at higher potential, this is at lower, this is at higher potential, this will at lower. When the end rings are connected, now the current starts circulating in these in such a way. Here is the concept. Let me repeat once again from the starting. We fed three-phase supply, to the stator of three-phase induction motor whose windings are 120 degree apart in space. We got the rotating magnetic field. Rotating magnetic field cuts the rotor conductors. EMF is there, EMF is induced. Since end rings are connected, so what will happen? Current will start circulating. Now current is circulating in these conductors, so now it is having its own magnetic field. So now we are having two magnetic fields, one is produced by rotor, one is produced by stator, and due to interaction of these two, torque is produced. And the direction of the torque will be such that according to Lenge's law, the direction of flow of current in these rotor bars will be such that it will oppose the cause of its production. Here was one important thing. If we are feeding 50 hertz supply, 50 hertz supply is given, and suppose this stator is designed for 4 pole. So the frequency of, so the speed of the rotation of this resultant rotating magnetic field is 120 F upon P. For 50 hertz 4 pole, it is coming as 1500 RPM. 120 multiplied by 50 divided by 4. So it is coming as 1500 RPM. So magnetic field is rotating with speed 1500 RPM. It is inducing current, it is inducing EMF in the rotor bars. As a result, now current is also flowing through the rotor bars. In the rotor, one magnetic field is produced. The only way, if the rotor starts rotating in the same direction as that of rotating machine, this resultant rotating field, only then this relative motion will be less. So the torque which is produced, it will try to rotate this. Now suppose rotor started rotating, and now the speed of this, suppose 200 RPM. Stator produced rotating magnetic field 1500 RPM. Rotor is rotating at a speed of 200. So now there is no relative motion. Is it? No. 1300 RPM, it is the difference. 1500 minus 200. So 1300 RPM is the difference. So due to that relative motion, again EMF will be induced in these rotor conductors or not? Yes, it will be produced. So end rings are there, so current will flow or not? Yes, it will flow. So more torque will flow, more torque will be developed. Now this rotor is rotating at 500. Now the relative speed is finished? No. 1500 and this is rotating at 500. Again there is difference of 1000. That means EMF will be induced in the conductor? Yes. Current will flow? Yes. So more torque will be developed? Yes. Okay. So now more torque, it is rotating the rotor like this, and now suppose speed is now 1200. Now there is no relative motion. 1500, this is rotating at 1200. Okay, still there is difference of 300. That means due to that relative motion, EMF will be induced in this rotor conductor? Yes, definitely. Faraday's law of electromagnetic induction, what does it say? Whenever there is relative motion between magnetic field and conductor, an EMF will be induced in the conductor, you like or not, but it will induce. So due to that, in this way the rotor keeps on. Now suppose rotor is rotating at 1500 RPM. Rotor is rotating at 1500 RPM, 1500 RPM. Rotating magnetic field is also rotating at 1500 RPM. So now there is no relative motion. So now at this condition, what will happen? Will there be any EMF induced in the conductor? No. What about the current? No current. So, what about the torque? No torque. So, what will happen? Now, it will come to rest. Now, since there is no torque, this rotor will slow down. Due to inertia, it will continue to rotate, but it will get slow down. Have you seen your bicycle? If you are not pedaling, then does it stop? No, it keeps on rolling due to momentum. Then again, when you pedal, then it will pick up the speed. So, since there was no torque, the speed is now somewhat less. Moment the speed is less, again what happens? Relative motion will appear. Then there will be EMF in the conductors. Then current will start flowing and the torque will be there. So, in this way, the rotor of induction motor always tries to catch that synchronous speed of rotating machine, which is given by 120 F upon P, Ns is equal to 120 F upon P, but it never succeeds. So, induction motor always runs at a speed somewhat less than synchronous speed. Suppose rotor speed is Nr, synchronous speed is Ns, then this difference is known as slip speed, Ns minus Nr, it is slip speed. And if we divide by Ns, that means Ns minus Nr upon Ns, it will become slip. And if you multiply by 100, it will become percentage slip, Ns minus Nr upon Ns into 100. So, today we have seen the constructional detail and basic principle of operation of three-phase induction motor. To conclude, let me revise everything once again. We are having three-phase winding on the stator. These windings are kept 120 degree apart. When we feed three-phase supply, we get rotating magnetic field. Just now recall my first example. When single phase supply was given, the type of field was pulsating standing. Magnitude was changing all the time, but axis was fixed. In case of three-phase motor, the magnitude of this is fixed all the time. Magnitude of resultant field, it is fixed, equal to 3 by 2 phi m, where phi m is maximum flux being produced by one coil. And speed of rotation is given by Ns is equal to 120 F upon P. So, if inside this stator, if I am inserting this type of rotor, it will become squirrel cage induction motor. Now, if I remove this, I am having another type of rotor also, that is known as slip ring induction motor. In slip ring induction motor, we are having 3 slip rings. Very soon you will see. So, if I am going to insert slip ring induction motor, then now this motor will be called as slip ring induction motor. What is the difference? In slip ring induction motor, we are having provision of insertion of additional resistance in the rotor circuit. Yes, it is very useful to increase the starting torque. Suppose overhead crane is there, you will find LT and CT, longitudinal travel and cross travel. You will find the motors which are used for these drives are cage type, and for hoist operation, when you have to pick up the load, for that the machine used is slip ring induction motor. If you remove cage type rotor, slip ring induction motor, if you are inserting a structure for provision of DC with DC supply and permanent some magnet, the same machine will become synchronous motor. In synchronous motor, it is doubly excited machine. From this end we are feeding AC, and for rotor we are feeding DC supply to make north pole and south pole. So, it is doubly fed machine. So, in today's class we have gone through the constructional detail and basic fundamental principle of operation of AC machines. In next class we will observe the methods of speed control, about the alternators, about the synchronous machine, and of course some starting mechanism and other basic fundamental which are essential for maintenance engineer to understand. Thank you.